So last time we've introduced the microcanonical ensemble and I discussed a connection between entropy and phase space volume. And what I was doing at the end of the lecture was an exercise showing you how to do calculations with the microcanonical ensemble for the ideal gas, which is what you see here in this slide. Now, before I start, well, this is something you will understand later on, but it's the microcanonical ensemble is not exactly the simplest possible ensemble to be used in statistical mechanics. Let me put it this way. The other two ensembles that we will introduce, the canonical and grand canonical ensemble, are much, much simpler to use. And that is why in most cases in statistical mechanics, calculations are done in a canonical or grand canonical setting, not in a microcanonical one. Now, before I start all the discussion on calculations done in the microcanonical ensemble and so on and so far, the reason I'm doing this exercise of computing things for the ideal gas, for example, in the microcanonical setting, is not that I want to teach you some techniques that could be useful for your, for example, research in the future. The microcanonical ensemble is very peculiar and typically is not being used. But it's useful to see how to do calculations in the microcanonical setting, because at the end of the day, we will prove later on that in the thermodynamic limit, calculations done in the three ensembles are equivalent. The three ensembles are completely equivalent in the thermodynamic limit. Therefore, when you have at hand a problem in statistical mechanics, you may freely choose which one of them use to do calculations, and then do calculations in your favorite ensemble. So doing calculations for the ideal gas in the microcanonical setting will make you appreciate later on, when we will redo the same calculation in the canonical and grand canonical setting, how much simpler it is to use the other ensembles as compared to the microcanonical one. Okay, so this is the motivation with which I'm doing calculations in the microcanonical ensemble, and I'm solving these exercises. Okay, so this said, what we said last time is that we are interested in computing the entropy for an ideal gas, which is described by an Hamiltonian, which is written up here, is PA squared over 2m. So it's an ideal gas, it's just a gas of non-interacting particles. The entropy is equal to K Boltzmann log of sigma, or log of omega, or log of gamma. We have seen that the three of them are equivalent. And then sigma is given by this integral. So integral for all over the phase space volume enclosed by the hypersurface of energy E. So this is this condition of the QdP. So these are 6n phase space variable divided by h to the power 3n, where h is some, for the moment, arbitrary constant with dimensions of an action. Okay. Now, since the Hamiltonian contains only p, then it's evident that the integral over q can be done. It gives us a volume to the power n. N is the total number of particles, and therefore we have v to the power n divided by h to the power 3n. The integral over all the dp, there are 3n of them, subject to the constraint that the h is smaller than e, and therefore the sum over I of pi squared is smaller than 2n times e. Now, If we think for a second about what I wrote here, this defines the volume of a sphere in 3n dimensions of radius r equal to the square root of sum over I pi squared, which should be equal, smaller or equal than 2m e. So the radius of the outer sphere that limits the phase space volume I want to calculate is square root of 2m times e. And then I told you, okay, so the volume of a sphere in n dimensions is something that you can, not so easily, but you can easily figure out what it is just by looking at standard books of mathematical methods or looking at Wikipedia. And the volume of a sphere in n dimensions of radius n, r, is given by this formula, where the constant is pi, Cn is equal to pi to the n over 2 divided by gamma n over 2 plus 1. And then you have the radius to the power n. So now, if you substitute the constants and the value of the radius we obtain that sigma of E is given by this expression. And last time we have done the calculation of showing what happens if you, if instead of computing sigma, you compute gamma, and that the two things are completely equivalent from the point of view of the leading exponential divergence with n, so the leading behavior with n in the thermodynamic limit. All right, so now we are ready to move on. So let me take this sigma, copy, go to the next page. We're ready to move on because once we have sigma, we can easily compute the entropy, S, which is K Boltzmann log of sigma, and which is equal to K Boltzmann times log of C to the 3n plus n log of V over H cube plus 3/2 n, or actually, let me write it this way, plus n log of 2m times e to the power 3/2. All right. So now, what is C3n? Well, C3n is written up and was written up and before, is equal to, just a second, is equal to pi to the power 3n over 2, correct? Yes, divided by gamma 3n over 2 plus 1. And now, well, if we take the log of this, let me write it better. If we take the log of C3n, this is equal to n times the log of pi to the 3/2 minus the log of gamma to the power 3n over 2 plus 1. And now I have to remember something, that gamma of n plus 1 is equal to n factorial, right? If n is an integer, correct? And in particular, we know So therefore, what you know as the Sterling formula, the Sterling approximation, is actually an asymptotic expansion. I'm using complicated words, but it's essentially the expansion of the log of gamma n plus 1 of the gamma function for large n, okay? Is the asymptotic expansion. So I can rewrite the Sterling approximation as this formula here. And now you see that if I use this for what I wrote here, what I obtain is that star is equal to n times the log of pi to the power 3 over 2 minus just a second, minus n log of 3n over 2 to the power 3 halves plus 3n over 2, right? You agree? I think it's correct. All right, so now if you take this expression here, plug it in here, and do all the algebra, which I leave you as an exercise, then you should be obtaining the following.
Sorry, Professor.
Yes.
Does this mean that the n must divide, like multiply of 2, so that the 3n over 2 is an integer?
No, I think so. Strictly speaking, I think this formula here. So, you can define the gamma function for any x, right? You can define the gamma function as log of gamma x plus 1. Gamma of x plus 1 is meaningful for any x. Correct? Have you ever seen a gamma function? You know what is a gamma function? Everybody knows what is a gamma function? Yes or no?
Yes.
Yes.
So let's do it this way. Is there someone who doesn't know what is a gamma function? Don't be shy. I mean, there is no problem. You're not supposed to know what is a gamma function. If you know, it's good. Otherwise, I explain.
But I met it before, but I just met it in case x is.
Okay, so let me just 1 second, 1 little second. Gamma function, here it is. So let's make a little parenthesis. All right, so the gamma function is essentially called a generalized factorial, right? Is a function that is defined like this. Gamma of z is equal to the integral between 0 and plus infinity of x to the power z minus 1 e to the minus x ex. Okay, so this is the gamma function. And this function has the property that gamma of z plus 1 is equal to z gamma of z. I mean, it's something that you can prove. Therefore, this implies that if z is an integer, right, n, then this identity means that this is nothing but the generalized, this is nothing but a factorial. If you iterate it, you see that what you get is a factorial, right? Now, what I wanted to say is that here, this expression here, this asymptotic expansion, I think it's correct for any n. N doesn't have to be an integer. And therefore, you can forget about the fact that n should be an even number that divides 2, right? It's not a big deal anymore. All right, so the Sterling approximation you're used to is a specific case of an asymptotic expansion for gamma functions. That's what I'm trying to say. All right. Good. So let me now move on. And so let me cancel this because it's useless. So let me now take these two guys and substitute into the expression for the entropy. And what I obtain is that S, so this is the final result, S is equal to K Boltzmann times N. I collected N everywhere in order to have something that is overall proportional to N, times log of V times 4 pi M times E divided by 3h squared N to the power 3/2, plus there is an additional term, 3n over 2 K Boltzmann. Now this term here comes from this term in the expansion of Cn. You see that if I add it here, I get 3n over 2 times K Boltzmann. So this is my final result. And now what do I do with this? Well, I have the entropy, right? Now, in principle, I can try to derive everything else. In particular, one thing I might want to do is try to derive the equation of state for the ideal gas, starting from this expression. So how would I derive the equation of state? Well, one thing I can do is compute the temperature, which is the derivative of the internal energy with respect to the entropy. Another thing I can do is compute the pressure, which is minus the derivative of the internal energy with respect to the volume. And then I can compare the two expressions that I get and try to get an equation of state, right? Now, you see that in order to compute these quantities, what I have to do is to re-express. Here I have the entropy S as a function of energy and volume. So what I want to do now in order to compute these two derivatives is re-express the energy as a function, the internal energy as a function of entropy and volume. Well, how do I do that? I just take the exponential of this, right? So I have that exponential of S over KBN minus 3/2 is equal to V times 4/3 pi M times E over H squared N to the power 3/2. Right? I just took this, took it on the other side, divided by K Boltzmann N, and exponentiated everything. So And therefore, you see that if I now take both sides of this to the power 2/3, I'm able to solve this equation for E and re-express E in terms of the entropy and the volume and the number of particles. The result is E equal to volume to the minus 2/3 times 3/4 h squared n over IM times exponential of 2/3 S over K Boltzmann n minus 1. Okay, so this is the internal energy. Now, it's important to notice one thing, that the internal energy depends exponentially on S. It's a simple exponent. Therefore, you see that if I compute the temperature T, which is dE ds, what I get is 2/3 times 1 over K Boltzmann times N times E itself. You agree? Everybody agrees with this?
Yes.
Good.
Yes.
And therefore the energy is equal to 3/2 K Boltzmann N times T, which is, by the way, a particular case of something much more general that is called the Equipartition Theory. Okay? Now I can compute the pressure, which is minus dE dV. This is equal to 2/3 E over V, and this is N over V K Boltzmann times T. Right? Because I substituted the value, the expression for the energy that I found before. And therefore, you see that what I obtain is quite neatly P times V equal to N K Boltzmann times T, which is our beloved equation of state for the ideal gas. Now, if you think for a second that this is just a consequence of the fact that here you have a volume to the minus 2/3, and here you have exponential of 2/3, the same constant, S over K Boltzmann N. All the other constants are inessential. Okay? Yes.
So also, as we know, for the internal energy for an ideal gas, which is CVT, so we can it's safe to say that that CVT is also proved. Am I correct?
In a sense, yes. Well, you can definitely compute.
Since we know that, okay, E is equal to CVT, and then we have E to be equal to 3/2 KB.
Yeah. I mean, yeah. So this, by the way, I think this formula is something that we used in thermodynamics at some point when we discussed well, the entropy of the ideal gas, right?
Yes, yes.
So now you see that it appears from a calculation. Now, it's interesting that you see, this calculation is it looks like a trivial calculation, and it is trivial, but it's actually a very deep result, because it tells you essentially that with the Boltzmann assumption, if you take a gas of non-interacting particles, which is what you expect to be your gas at low densities, when the particles are very far apart, then you get an equation of state, which is the ideal gas equation of state. So in other words, the Boltzmann formula that we wrote down is the correct connection between, or appears to be the correct connection between the microscopic world as represented by this Hamiltonian, right? This Hamiltonian is fully microscopic, and the macroscopic world as represented by this equation of state. Okay? It's the first time that you see this connection appearing. Now, the whole statistical mechanics is about this connection and tools, how to make this connection, transparent. All right. So before moving on,
Sorry.
yes.
Yeah, sorry to, I didn't get something you said quite earlier. I should have asked earlier. You said to us that the microcanonical example is quite not good to convenient. And why is that? Could you give insight a little bit about that?
Well, I can explain you in 2 seconds. I mean, I'm jumping a bit forward, if you want. So,
Okay.
but these are things that most of you already know. You, in particular, all of you know what is a partition function that describes a canonical ensemble. It's going to be phase space volume e to the minus h over kBt. You see that if here h, instead you substitute h dh for the ideal gas, which is sum over I pi squared over 2m, this partition function is just a Gaussian integral. Now, once you have a partition function, so this can be calculated in just by looking at it. I mean, Gaussian integrals are the only things in physics that you know every physicist should know by heart. And by the way, I never remember them. I mean, I never remember all the prefactors. I always to look them up. But it's easy. I mean, a Gaussian integral is something that can be done. Now, the interesting thing is that then, from the Gaussian integral, how to get all the thermodynamics in the canonical ensemble is straightforward because it comes from the formula that the Helmholtz free energy is, so the partition function is the exponential of minus beta times the Helmholtz free energy. Sorry. Yes. So, and therefore in 2 seconds you find the Helmholtz free energy and then you find everything else.
Yes.
So I'm just saying, so all these anticipations are just meant to say the following: calculations and the derivation of the equation of state for the ideal gas in the other 2 ensembles, canonical and ground canonical, are much simpler and much quicker.
I see.
While in the microcanonical ensemble, calculations are a bit more involved. That's why the microcanonical ensemble, though it's the most fundamental ensemble, is not very practical, strictly speaking, to do calculations. Okay?
Yes, I see. Thank you.
No problem. Okay. So let us now do together another ensemble, another exercise. On the microcanonical ensemble. Okay, the exercise is the following. I want to consider an Hamiltonian H, which is given by sum over I from 1 to n, H sigma I, where sigma I is equal to plus or minus 1. Okay, so this is the Hamiltonian that describes a bunch of non-interacting spins in a magnetic field, right? You agree? Now I want to compute the entropy for this Hamiltonian. Entropy. So the entropy is equal to K Boltzmann times the log of what in this case? I'm working in the microcanonical ensemble, therefore I have a given energy and given number of particles and of course given volume. I mean, my spins are sitting in on a certain lattice. So my entropy now for this particular setting in which I have discrete degrees of freedom is equal to K Boltzmann times the log of what? I cannot define gamma phi, right? Nor sigma, nor omega, because I don't have a gas. What should I put in here?
I think the demagnetization H.
No. Think about what is the basic idea, what is quantifying gamma phi? The phase space volume, what is telling you roughly? If I divided the phase space volume by a certain h to the power 3n, so I take my phase, as I have done, in the past, I take my phase space volume and I count the number of cells once I discretize it in a certain way. What is this gamma phi telling me? So let me rephrase my question. Gamma phi was equal to the integral E smaller than h smaller than e plus delta dq dp h to the power 3n, right? So it's like taking an hypersurface like this, and what I do is I slice it into some cells. Each cell has a volume, each cell, like each one of them, has a volume h to the power 3n. And this thing here is just the number of cells. So what is this number of cells in practice? What is counting the number of cells? I'm telling you. It's counting the number, as we have done in that example in thermodynamics, is roughly counting if you assume a resolution of your phase space volume h to the 3n, is counting the number of ways, the number of configurations, of microscopic configurations of your system that are consistent with the macroscopic conditions of having a constant E, constant number of particles, and a constant volume. I repeat, is the number of configurations, microscopic configurations, consistent with the macroscopic conditions. Okay? This is what is sitting in the log of the Boltzmann formula. A number of configurations with energy E. Okay? Is that clear? Yes or no?
Yes, it is. I think I've.
Sorry.
Yes.
What is
Yes.
H? Is it H to the power 3n, the volume of one cell in this
Yes,
picture?
H to the power 3n is the volume of one cell.
Okay.
Yeah. Is the volume of one of these guys. All right. So now that we understand this, now we know what, if we want to do a calculation, can I erase this figure? I can, right? If we want to do a calculation in the microcanonical ensemble, now we know what should be done. If I fix the energy, what I should do is compute the total number of configurations of my spin system that are consistent with that given energy, right? Okay?
Yes.
Now, each configuration here, I don't have a phase space volumes or things of that type. My phase space is completely discrete. And a phase space point is not indicated by a series of vectors qi, pi, but is indicated by the values of my discrete variables sigma 1 all the way to sigma n that can be equal to 0 to -1 or +1. Okay? So given a phase space point, the energy corresponding to this configuration is given by this formula here. And then it can be simplified in the following way. This is equal to H times the number of spins that are pointing up minus the number of spins that are pointing down. Okay, so this is my energy. And now if I fix this to be equal to a certain E, it is clear that fixing the energy is equivalent to fixing the difference of n up minus n down, correct? So in particular, n up plus n down is equal to n. And n up minus n down is equal to E divided by H. And now I can ask myself, how many microscopic configurations correspond to a given n and a given E? Now, if I rephrase this question in terms of n up and n down, this corresponds to the following question. How many number of configurations, how many microscopic configurations correspond to a given n up plus n down equal to n and n up minus n down? Well, so does someone have an idea? Is there someone good in combinatorics that can give me an answer? How many?
It's the binomial coefficient.
The binomial coefficient, that's right. So it's essentially, I mean, the answer to this question is the following. If I fix a total n up plus n down, and I want to have a certain value for the difference, this is equivalent to asking me how many ways do I have to put n down particles in n slots. And this is equal to n choose n down. So this is n factorial divided by n up factorial n down factorial. Okay? All right. So therefore, if this is the number of configurations, it is evident that the entropy is equal to K Boltzmann times log of n factorial divided by n down factorial and up factorial. Now, given this, what you do is you use Sterling. Use the Sterling approximation. Assume that the energy is not too close to the boundaries of your. So the total energy here can vary between plus n times h when all spins are up and minus n times h when all spins are down. Now assume that the energy is not too close to these boundaries, in which case both n and down and n up are large and scale in a certain way towards the thermodynamic limit. Then I can use the Sterling approximation to obtain that this is K Boltzmann times n log n minus n up log n up minus n down log n down. Okay? Now, let me go back to this, to these two conditions. If I have these two conditions to be satisfied, then it is evident that I must have that n up is equal to 1/2 n plus e over h, and n down is equal to 1/2 n minus e over h. Okay? Now, if I take these two expressions and substitute them here, so let me write it in green. Substitute. What I get is the following. What I get is that this is equal to K Boltzmann. K Boltzmann n log of 2 minus n over 2 log of 1 minus e over hn squared minus n over 2 e over hn times log of 1 plus e over hn divided by 1 minus e over hn. All right. So, given this expression, I can, for example, compute what is the temperature, 1 over T. So this is equal to ds dE. And this is going to be equal to K Boltzmann divided by H times the arc tangent hyperbolic of E divided by h times n. And this makes a lot of sense because it tells me that essentially, if I invert this formula, it tells me that the internal energy is equal to n times h times the tangent hyperbolic of h over kBt. Now,
Excuse me, Professor.
yes, yes.
How can we see the difference of
How can we see that?
how can we see the difference of spin up and spin down? Is
I didn't sorry, can you write your question because I don't understand it. Can you write it in the chat?
Okay.
Please write your question in the chat because I don't understand it. Are you writing? Ah, here it is. How can we say that the difference of spin up and spin down is E over H? Well, that is just a consequence of the definition, right? Look at this. My Hamiltonian is H times sigma I, sum over I. Now, every time I have a spin up, I have a contribution to this energy, which is plus H. Every time I have a spin down, I have a contribution, which is minus H. And therefore, it's evident that the total energy is going to be H and up plus minus H and down, right? Which is H and up minus and down. So this is going to be my total energy, right? You agree?
Yes, thank you.
So now you see how it works. All right, so now if you invert this formula, you find this, which is, by the way, something that we will find later on when we will be computing the we'll be doing the same calculation in the canonical ensemble. Now, suppose that we have done this calculation and this was the final exam, right? And now I want to check myself. I want to check whether this result is correct or not. So how do I do it? How do you check whether this result is correct or not?
You can check if it's extensive. Or...
It is extensive, right?
Yeah,
You see that it's proportional to m, so that is fine. It is extensive. Another thing you can check is the limits in which the temperature is very large or the temperature is very small, right? That can be done. Now, suppose that the temperature is very large, right? So what do you expect if the temperature is very large? If the temperature is very large, any physical system is maximally disordered, right? if the temperature tends to infinity, which means that you have equal probability of each individual spin to be pointing up or down, right? And therefore, you see that if the temperature is very large, that the internal energy should tend to zero, because if you have equal probability to be up or down, the average energy for each individual spin is going to be zero, and the sum of them is going to be zero as well. And you see that if I take the limit of t going to infinity in this formula, I get zero, right? So everything is fine. Now, if instead I take the limit of t going to zero, of temperature going to zero, then the state that should win is the state of minimum energy, which corresponds to all spins pointing in the direction that is opposite to magnetization, which makes me suspect that there is a minus sign missing somewhere, because I should get that for temperature going to zero, so the tangent hyperbolic tends to 1, right? But I should be getting an energy which is minus n times h. So probably I made a mistake somewhere, and there is a minus sign here. So I invite you to check it carefully. So you understand that the idea is the following. When you do a calculation and you get to a final result, of course you check yourself by seeing whether this result is extensive or not, whether it satisfies the simplest possible properties that you expect from the physical quantity you're calculating. But another thing you can do is take limits of this result and go towards limits in which you can guess what is going to be the value of this quantity, right? So we know, for example, high temperature, maximally disordered, average energy zero. Zero temperature, all spins are pointing down. The energy is minus n times h, and so on and so forth. You see what I mean? So keep thinking this way when you solve exercises, okay? And also when you will be preparing yourself for the final exam, get ready to always check the various limits. We will be doing it all the time. So at the end of the day, it's going to be automatic for you to take limits. But what I'm saying is that once someone asks me whether I care about the derivation in an exercise or whether I care about the final result. And I told you, for me, what is important is to see that you're thinking like a physicist, right? And even if you get a final result that is wrong, but you're able to tell me by taking limits and checking yourself, there is a problem in this final result because it doesn't match my expectation in the limit of blah, 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 that counts. That is an important statement. So please start thinking this way.
Sorry?
Yes?
Why did you say what when the temperature goes to zero, all the spins are down?
Why?
Why all the spins are down for temperature zero?
Because you should go to the state of minimum energy.
Okay.
The temperature goes to zero.
Mm-hmm.
And I think the state, if I'm not mistaken, the state of minimum energy for this amount is the one in which all spins are pointing down.
Yes,
Right?
sure.
Because
Yes.
it's minus n times h.
Yes. Thank you.
All right. Okay,
sorry.
so
Sorry.
yes.
So for in the limit when temperature is going to infinity, that we have equal probability for spin up and down.
Yes.
Okay.
Yes. Yeah, we have equal probability. All right. So let me now finish this lecture by proving for you an interesting theorem It is called equipartition theorem. Now, the equipartition theorem says the following. Suppose that I have an Hamiltonian H, which is a function of phase space variables Qi and Pi. Then the average with respect to the microcanonical ensemble of Qi, dH, dQi, dQj in the microcanonical ensemble is equal to delta ij kbt. So this is the statement of the equipartition theorem. Now, let me prove it for you and then show you what are the implications. Well, this average is defined as follows. So let me put a line here. Is defined as integral E smaller than H smaller than E plus delta dq dp qi dh dqj, and then integral E smaller than H smaller than E plus delta dq di. So this is what is meant by that average. Now, you can rewrite this as 1 over gamma of E. Now, if delta is small, I can rewrite the upper integral as delta and then the derivative with respect to the energy of the integral H smaller than E dq dp qi dh dqj. Okay. If you're not convinced of this formula, think about the story I told you last time about the two shells. The two, so the calculation we have done about the two shells, right? If delta goes to 0, the integral over a shell can be seen as delta times the derivative with respect to the energy of the integral over the sphere, over the entire volume of the sphere. All right, so now this is equal to what? This is delta over gamma dDE. And now I do the following, I integrate by parts. So this is the integral H smaller than E dq dp. Then I write it as ddqj. No, sorry. Before I do this, before I integrate by parts, I can rewrite this as dq dp x, sorry, not x, but qi dqj h minus e. Why I can put a minus e there? Because, of course, when I take a derivative, I get 0, because e is a constant that doesn't depend on q. So I didn't do anything. So now I take this and I do what I was doing before. So I rewrite it as dd integral h smaller than e dq dp, and then what I have is dqj, then qi h minus e minus, well, minus the derivative dqj acting on qi, right? That gives me delta ij, and then integral h smaller than e of dq dp. Let me put it down here, h minus e. All right, so now,
Sorry.
yes.
Can you explain why did you put qi inside the derivative?
Well, so here, let me see it this way. Here I have qi d dqj of something, right? So this I can see it as dqj of qi times something minus, or let me explain it this way. D dqj qi times something is equal to delta ij, because it's dqj qi times something, plus qi dqj of something. This something is h minus e. So you see that I want to compute the integral of this, but the integral of this is equal to the integral over of this total derivative minus this guy. You see? This is what I wrote here.
Yes. Sorry, the last line is not clear in the screen. It's not visible.
It's not visible. Okay, let me, I'll show you in just a second.
Okay.
So now you can see it, right?
Yes, thank you.
Actually, let me even do this. Oh, yeah. All right. And now this is equal to what? Well, now this is an integral of a total derivative, right? So it's like an integral dx f prime of x, right? It's a total derivative. And therefore, it's just the integration at the two boundaries in the direction j. But the point is that the two boundaries in the direction j are delimited by the hypersurface of constant energy E, right? And therefore, at the boundaries, H is equal to E, which implies that this integral here is going to be equal to 0. So what remains is only the other term.
Sorry, sir.
Yes?
Will you repeat, please, what you just say about H and E?
Yeah, so what I'm saying is that this is a total integral, sorry, the integral of a total derivative, right? And therefore is the value of this function at the boundaries. of the integration region. But the boundaries are determined by the hypersurface of constant energy E, according to this formula, right?
Yes.
And therefore, at the boundaries, this function here that contains h minus e is equal to 0, which implies that the integral itself is equal to 0. You see?
Yes.
Therefore, the final result is delta over gamma dE of delta ij integral h smaller than e dq dp e minus h. Right. And now I take the derivative. Now, now I take the derivative. Just a second. Yeah. Now I take the derivative with respect to e of this integral. Now, when I take the derivative with respect to e is appearing both on the boundary of integration and on the integrand itself, right? Now, let's think about when this derivative acts on the boundary of integration. Suppose that I give you an integral between 0 and x dy f of y. And I take a derivative with respect to x. This is equal to what? Is equal to what? This derivative is equal to what, guys?
Fy, f big.
F evaluated in
fx minus f0.
fx minus, no, it's actually fx because f. Right?
Yeah, I think it's fx plus the integral of dy ddx of fy.
Absolutely, but you know, in this particular case, I assume that fy does not depend on x. So
okay.
if it doesn't depend on x, then this is the result, right? You agree?
Yes.
So now, you see here, if I take the derivative with respect to e acting on the boundary, I get the value of the integrand evaluated at the boundary. But again, the integrand evaluated at the boundary is equal to 0, right? Therefore, the derivative acting on the boundary value gives me 0. You agree?
Yes.
Okay. So therefore, this derivative is going to be equal to delta over gamma, delta ij, integral h minus e, dq, dp, dde, e minus h. But now this derivative is equal to 1, right? This is equal to 1. And therefore, what I get is delta over gamma, delta ij, times the integral for all h smaller than e, dq, dp, or in other words, I get delta ij, sigma divided by gamma. Okay? Or delta ij sigma divided by what is gamma of E divided by delta in the limit of delta going to 0? This is equal to the derivative of sigma with respect to the energy.
Yes, which is
okay.
Yes.
So this is d sigma d, or in other words, this is delta ij, the derivative with respect to the energy of log of sigma to the power -1. Which is equal to delta ij times k Boltzmann times the derivative of the entropy, of the Boltzmann entropy with respect to the energy to the power -1. And this is by definition delta ij k Boltzmann times t. QED. Have you ever seen this QED? You know what it means?
Yes, it means what we want to prove.
What for quod erat demonstrandum? Since you're in Italy, I can use Latin. Okay. What we want to prove. Quod erat demonstrandum. Excellent. So, so that's it. Now, this theorem is actually quite interesting because it tells us something very important. Well, first of all, there is a, since we are playing the game of being mathematical, let's write a corollary, A. So corollary A is that, so Pi dPj or dPi H is equal to Qi dQi H, which is equal to kBt. This is always equal to kBt. But most importantly is the corollary B. So the equipartition theorem is useful because it allows you to immediately write down what is the average internal energy for quadratic Hamiltonians. What is a quadratic Hamiltonian? Quadratic Hamiltonian is an Hamiltonian, sorry, H, which is equal to sum over I, AI, PI squared plus sum over B, I, BI, QI squared. Right? So it is a sum of quadratic terms. The Hamiltonian for the ideal gas is a specific case. You might have also the Hamiltonian of a series of harmonic oscillators, of even of interacting harmonic oscillators. It doesn't really matter. It's always a quadratic Hamiltonian. Now, the reason you can write down immediately the internal energy for a quadratic Hamiltonian is that if you look at it, the quadratic Hamiltonian can be written as 1/2 sum over I pi ph dpi plus sum over I 1/2 qi dh dqi, right? I mean, just take the derivatives and you see that what I wrote is correct. And therefore, the average of your internal energy in the microcanonical ensemble, if you use the corollary A, is equal to what? Is equal to F divided by 2 times kBT. Or if you want, F is the number of quadratic terms in the Hamiltonian. Now, if you have a many particle system, so in which your Hamiltonian is the sum of identical Hamiltonians for n particles, you can rewrite this as, actually, I don't like this notation. Let me write it like this, F. You can write it as n times F over 2 kBT. So n is the number of particles. F is the number of active variables or degrees of freedom, call it the way you want, per particle. And kBT is what you get for each one of them. So, for example, if I have free particles, right, free non-interacting particles, then F is equal to 3, because I have the 3 directions of momentum, P1, P2, and P3 squared for each particle. If I have particles that are sitting in an harmonic potential, then F is equal to 6, right, in 3 dimensions, and so on and so far. Now, this, the applicability of this theorem is actually, unfortunately, limited to yeah, to quadratic Hamiltonians. Now, the reason it is limited to quadratic Hamiltonians is actually very, very simple. If you would have, so there was a guy, actually, a diploma student before you. His name was Joel. Now, I told you that I hardly remember names. No, the only reason I remember his name is that in my notes, I have the question he asked me written up as Joel Theorem. So he became famous. He has a theorem under his name. And Joel Theorem tells me the following, that if your Hamiltonian is a constant times the sum over I qi cube, right? Then the average microcanonical energy is, of course, equal to K Boltzmann T divided by 3, right? Now, so why, before I said that, strictly speaking, the real applicability of the equipartition theorem is limited to non-interacting systems? Well, the reason is very simple, is that in physics, the kinetic term is quadratic. The potential term in the Hamiltonian can be whatever you want. You can have a cubic term, a quartic, something very complicated and nonlinear. It doesn't really matter. But the kinetic term is always p squared over 2n, right? And the reason it is like that is that you want to get Newton equations. So therefore, it's natural that once you constrain the kinetic term to p squared over 2m, then of course also, if you want to apply to apply the equipartition theorem with the same prefactor, you see this 1/2 here, you have to have a quadratic term also in the potential term. Now, of course, if you don't have a kinetic term in your energy function, well, then you can do whatever you want, right? You can apply also this funny theorem to many other cases, but yeah, so it's much less relevant for significant physical situations. Okay. All right, so we are essentially done with the microcanonical ensemble. So next time we will do the canonical ensemble and then show the ensemble equivalence and do tons of exercises with the canonical ensemble. I will be essentially solving zillions of Hamiltonians and all sorts of calculations. Okay, so do you have any questions?
Professor?
Yes.
What's the connection between Joel theorem and corollary B?
Well, you cannot apply. So Joel theorem is fine if you have just a potential term of this type. But you see that if your H is equal to P squared over 2M, or P squared, well, let's put it, AP squared plus BQ cube, then you see that it doesn't work anymore, right? Because this is equal to A over 2, this is equal to 1/2 P dpH plus 1/3 Q dqH. So, well, you get a complicated right?
Oh, so in case of Joel theorem, the corollary B doesn't hold. Yeah?
No. Yeah, but forget about Joel theorem, and we will never be using it. So let's. What I meant to say is that essentially you're dealing we'll be using the equipartition theorem for quadratic Hamiltonians. And it's going to become important later on when we will be doing the black body radiation, the difference between quantum statistical mechanics and classical statistical mechanics. All right, guys. So that's it. I think we are done for today. So I'll see you next Wednesday with the canonical ensemble. Okay?
Okay.
Okay. Bye-bye.
Okay, goodbye.
Bye. Thank you.